How y'all feeling? Does anyone have any questions before we get started?
I have a question.
All right.
I was doing torque problems yesterday and I just got confused, figuring out, for clockwise and counterclockwise, how do you know which one's supposed to be positive and which one's negative?
You kind of just have to pick one and stick with it. Like, as long as your system is consistent, where all clockwise is, say, like if you pick clockwise to be positive, then all counterclockwise has to be negative.
Okay.
Is there a specific homework problem you were looking at?
Yeah, let me pull it up real quick. Chapter 8.
Which one was it?
Okay, go down a little bit. I think it was the very last one where there was like a hint button. Yeah.
Okay.
I didn't get that. Let me see. That might be it.
I don't think this one involves torque directly.
Okay. Maybe it was in the quiz.
Possible. This one?
Yes.
All right. So, for this odd shape, there are two clockwise forces and two clockwise torques and one counterclockwise torque. So, whatever sign you give these two, they need to have the same one, and this would be on the opposite side. So,
Why would they have the same sign?
these two?
Yes.
Well, that is because they are generating torque in the same direction.
Okay.
So, even though the forces aren't in the same direction, they would still make this thing, both of these would make it spin clockwise. Whereas this one would make it spin counterclockwise. So the torque generated by this one by itself, would need to be, is opposed by these two torques. And so for this question, you want to find the net torque, this torque plus this torque minus this torque. They give you a specific, assume that positive is counterclockwise. Interesting. So actually, what I just said is true. However, it wants the opposite sign. So I suppose actually to get that negative there, one, you can just make it a negative answer. You can do it the way I just said, make it negative. But what this is technically looking for is this one minus this one minus this one. So as long as these two have a different sign to this one.
Okay.
Figuring out what's clockwise and counterclockwise is just something that I find takes practice. But I find that sometimes it helps to kind of use like a pencil as a radius. So radius of the wheel here would be vertical, and physically take a force and push in the same direction, and then just note what direction it's spinning in. So that one's clockwise. This one also clockwise. And then this one counterclockwise. Same kind of works for, seesaws as well. So you can use your pencil as a physical tool. Does that help with this one?
Mm-hmm.
Okay. Anything else on your minds here at the start?
Okay. Well, on Monday, we started looking at chapter 9, and we're probably going to close that out today. Just to quickly review what we looked at. That's not the right button. Chapter 9 is about pressure and buoyancy. The things we went over on Monday were redefining density, because it comes up a lot in these formulas. And then going over the physics definition of pressure. Pressure equals force over area. Pressure is often caused on planet Earth by being submerged at some depth within a fluid. And this formula can tell you the pressure that that fluid adds when you are submerged in it based on its density and how much fluid is above you. And last thing we looked at was the definition and formula for buoyant force. The idea that when you are submerged in a fluid, because pressure increases with depth, the inward, upward pointing force on the bottom of an object is going to be stronger than the inward, downward force on the top of the object, creating a net force upwards, and that's where buoyant force comes from. My plan for today is to just practice all that information. I got a few more sample questions and one extra thing that I'll talk about towards the end, just as an extra application of all this stuff. So any questions or issues before we get started? I know I ask for questions every 5 minutes. I apologize if it gets annoying, but I really do. Just want to know if you need anything.
I have one more question.
Okay.
It's about, for kinetic energy angular, is the I-9 equation impulse or inertia?
Moment of inertia.
Okay.
Yeah, sorry. You can always ask if the formula sheet is ever unclear. Again, physics ran out of letters a long time ago. All right. So let's first look at definition of pressure and also pressure at depth. Something that sea divers and people who build deep sea equipment have to keep in mind is whether or not something can withstand the pressures at a certain depth. So we're going to build a deep sea drone, and given that these things are electronic, you have to protect the electronics from the water. So we're going to seal all those electrics inside of a glass dome, glass sphere. Said sphere is going to have a surface area, exterior, total spherical surface area of 0.9 meters squared, and when pressurized at Earth's surface, it can withstand it will break if you add a force of 3,000 newtons to it. That's the force it can take, at which point it will shatter. So, given those pieces of information, what pressure will break the sphere? What added pressure? It's built equalized at Earth's surface. What additional pressure beyond atmospheric pressure will shatter this thing? Yeah. Pressure is force over area. You take the force that will break it over its surface area. And that tells us how much added pressure will shatter it. Now, that's not the total pressure that shatters it, because on Earth's surface it's already subject to atmospheric pressure. That's the pressure above atmosphere that would break it. So, with that pressure determined, how deep in the ocean can this thing go before breaking? Yep. Very poorly designed, as it turns out. That's the added pressure that it can handle, or not handle, technically. That's going to be the pressure created by being at a depth within seawater. Seawater is slightly denser than fresh water. And H turns out to be 0.33 meters. 33 centimeters, and it breaks. Or more realistically, it starts leaking, and then you short out. So, not very well designed. Back to the drawing board on this one. And real quick, if that is the pressure 33 centimeters deep into water, just from the water, what is the true pressure that deep? Whenever the homework mentions true pressure, that's basically just the pressure added from the fluid plus whatever the atmospheric pressure is above that. So true pressure is simply referring to the real total. Most things on the surface are built and grown such that atmospheric pressure doesn't bother us. We're equalized for it, so it doesn't especially matter, but some instrumentation you do have to know what the true pressure is. So the true pressure down there only goes up by slightly more than 3,000, so it is not a very big pressure increase. A human probably wouldn't notice it very strongly. And yet, this thing starts leaking and cracking, which is, again, not a very well-designed sea drone. Yes?
How do you calculate air pressure? Is that a given?
Most sciences just assume and consider standard atmospheric pressure at room temperature, at Earth's surface, to be a given of 101,325 pascals. I would list that as a constant where it's needed. You don't necessarily need to memorize it, but it's considered to be a constant, kind of like 9.8. That value does fluctuate, again, based on temperature and elevation. So it's not a constant thing acting on you. And in fact, some people that are sensitive to pressure can probably notice pressure shift due to, like temperature and weather and things like that. I can smell rain. I think that's either pressure or air ionization. So any questions for this one? All right. Now, separately, let's also look at buoyancy. Actually, no, real quick, before that, there's something related to pressure at depth I wanted to mention on Monday and forgot about. Have you ever noticed that dams are shaped like this in profile? To illustrate the point, if you haven't looked at a dam recently, I don't think there's any around here. Here is the Hoover Dam. On the inner side, it is flat all the way down to the bottom, but on the dry side of it, note how it curves outward. It's slight and gradual, but it does extend physically out, kind of like a sine, like a geometry function as you go down to the bottom. And that's because since water pressure increases with depth, it's thicker at the bottom to reinforce against the greater pressure. So, a related consequence of P equals rho GH. All right, that was just on my mind since Monday. The other thing we talked about Monday was buoyancy, so let's get a little more practice for that one in too. Submarines can manipulate their buoyancy. They do this by pulling in seawater. Basically, they're able to control their net density because the empty tank is way less dense than the tank is when it's full of seawater. So here we have a poorly drawn submarine. Most of it is underwater. Specifically, 4/5 of it is under the water. That'll become relevant later. And that's true of most boats, actually. An amount of them has to be under the water, whereas the rest of it is above the surface. And this thing has a mass of 43,000 kilograms. So it certainly doesn't float because it's light. So, first question, what is the needed amount of buoyant force for this thing to float by itself on the surface? Not quite. What are the rules that determines if something floats or not? Yeah, force up has to equal force down. And if this thing is just floating by itself unassisted, force down is gravity and the force up is buoyant force. We can't really determine its buoyant force without knowing its volume, but using the normal formula we can't. But we know its mass. We know how much it weighs. And therefore, the buoyant force up has to be at minimum equal to that weight so that it is not sinking, assuming that there's nothing else holding it up. So remember, net force equals mass times acceleration. There are two forces here, buoyant force up and gravity down. And if you're floating as stationary as you can in the ocean, what is your net acceleration? 0. If you're accelerating in the ocean, it means you are either zooming forwards or sinking. So if those are the only two, they have to cancel each other out. So buoyant force is the opposite of gravity. And if we know its mass, we can find its weight. And therefore, indirectly, buoyant force. Bless you. So this thing weighs and therefore requires 421,400 newtons of force to keep it at the water's surface, same as its weight. So again, it doesn't float because it's light, as most ships are not. Any questions determining that number? For further context, I think I found earlier that was about 50 tons of metal. So again, heavy. And at least when I'm teaching, or when I'm talking about this sort of thing with younger people, one of the questions I get pretty often is, why does the metal float in the first place? 50 tons of pure metal would have a certain volume, but it's not one solid chunk. They shaped it into a boat hull, so it takes up more space than it would if it was a compressed pure block. So that kind of drives down the total density as long as you don't have a leak. So if you've ever thought about that, that's why metal can float. Now, if that's the required buoyant force, how much of this ship has to be underwater to make this happen? What volume of ship is underwater to necessitate this buoyant force being created? The other formula for buoyant force is FB equals rho VG. And now that we have a number for buoyant force, we can figure out the boats. I keep calling it a boat. Subby is just a boat that can go under the surface, really. Yes?
21.9 meters cubed.
Mm-hmm. I use density of seawater because it's always the fluid's density, not the density of the object. However, we do want to find the submerged volume of the object, and that's what the V in this formula is. The amount of it that is under the water. And the submerged volume of this particular object about 42 meters cubed. Which I should just get a normal 1 meter long meter something here. 1 meter cubed is this by this by this. So 42 of those things stacked into a livable space. Which might sound okay, but remember that a lot of that space is made up of walls and machinery. So it's not all living space. That's why they pay good money to live on a submarine, because it's awful. Now, last question. That's the submerged amount of this boat. If 1/5 of the entire thing is still sticking out of the water, what is the total volume of the vessel? What would you do to that number to find the total volume if 1/5 of it is not included here? Yep. Whatever the total volume is, that number we just found is 4/5 of it. So we can get the total volume back by multiplying that number by 5/4. So about 52.5 if you include the part in the air. No space for a breakfast nook. And if you were building something like this, you would need to know the total volume, since once you take in water and sink, the whole thing would be underwater and you'd have to factor in the changes in buoyant force. But they are able to sink by pulling in water, increasing their weight, and that would, the goal being, if weight is bigger than buoyant force, you sink until they equalize. So, questions? I can give the type of question you might see on your homework. All right. How's this stuff felt overall? All right. Well, there's only one more pressure-related thing that I want to talk about. It's kind of just an extension of what we've been doing, and it'll be the last new thing before the test. So on Friday, we'll be reviewing chapter 9 and then all the test stuff as a whole. So with this, we'll close out our learning before test 2 and before Thanksgiving. I want to look back briefly at the definition of pressure real quick. Pressure equals force over surface area. If pressure acts on an object's surface area, it generates a certain amount of force per that area. And I am, again, under the general consensus that most of my students are either majoring in chemistry or still have to take an amount of chem classes for something else, correct?
Now, when I took chem, I had to deal with a lot of gases sealed inside of containers. What I'm going to try to draw here is something resembling a helium tank. So, gas sealed inside of a container, usually you might consider, say, how many moles are in there, what temperature it's at, what pressure it's at, things like that. And a pressurized helium tank that you get at your party supply store of choice, it's pressurized because there's more gas in there than there's supposed to be, and it takes a certain amount of pressure to hold all of it in. That pressure inside means that the gas itself is going to exert force outward on every wall of the container. And the same pressure can actually create different forces on different parts of the object based on the surface area of that part of the object. So the flat bottom piece, most of these things have a flat part underneath so that it sits on the floor. This lower part should have a bigger surface area than the nozzle at the top, if you just consider the two parts here to be circles for simplicity's sake. This is just physically a bigger circle at the bottom than the output valve. And as a result, there's actually the same pressure applies more force to the bottom than to the flat parts of this valve. And that's usually why the metal at the bottom has to be a lot thicker to account for that increase in force. So the same pressurized system can exert different forces on different parts of the system based on the applied surface area of that part of the system. Good so far? All right. Now, humans have figured out a pretty interesting application for this over the years. Hydraulic systems, which, until combustion and electric motors was the best way we had to make things move using machines. Let's say you need to move a car. You need to lift a car. You as a normal human, please let me know, are you capable of lifting a car with your bare hands? Darn, I was hoping someone was. Yeah, I certainly can. It takes more force because to lift a car, you have to exert a force equal to its weight, which cars have a lot of mass. They tend to be very heavy. No human I know of could lift an SUV like that barehanded. However, with the assistance of a certain machine, pressure, and Pascal's principle, you too can lift a car indirectly with your bare hands. This is kind of a mock-up of a type of apparatus you might find built into the floor of a car shop, because that's the kind of place where you need to get a car about 10 feet in the air to be able to see what's underneath it. They don't do it with their bare hands. They have this thing built into the floor of their garage. This is a reservoir of liquid, pressurized. So not dissimilar to the helium tank, but it's liquid instead of gas. And this system is basically two pistons connected to a fluid reservoir. And when I say piston, I just basically mean a cylinder with a moving part that can go either up or down, pushing down on the liquid or where the liquid pushes up on it. And the two different pistons here have two very different cross-sectional surface areas. I'm going to try to draw this a little more three-dimensionally because I'm a very visual person and my brain has a hard time seeing it sometimes. So try to make the same basic picture look a little more 3D. This is the fluid reservoir. We've got two cylinders attached either side. The fluid within
extends up into the cylinders, and resting atop the fluid on either side is a piston cylinder. And because the two sides have very different diameters, they also have very different circular areas. So like the area of this circle is just way smaller than the area of this circle. And what's gonna happen here is the liquid is gonna exert the same pressure on either side of this system. However, because the two different sides have very different areas, you're gonna get a different amount of force out of either side. It's the same liquid on the both ends, so both sides have the same pressure. But pressure is force over area, meaning that the side with bigger area can output more force for the same pressure than the narrow side. Narrow side, same pressure, but drastically reduced surface area, smaller force requirement. So a machine like this can basically multiply your force to let you lift a car indirectly with your bare hands. Keyword's indirectly, but still. Now, the way that this works for this particular apparatus is we've got a 650 kilogram SUV on the larger of the two pistons. That piston has a circular, flat internal area of 2 meters squared. So that's the area over here, the area of this piston, the area of that circle. And then the other side, this circle has an area of 25 centimeters squared. Since we like meters in here, are we going to plug in 25 centimeters squared? Are we going to plug in instead? Almost, because it's centimeters squared to meters squared. And if there's an exponent on the unit, you have to convert it more than once. So, real quick. 100 centimeters to 1 meter. If you divide by 100 once, you only canceled the squared, not the centimeters squared. So this would be centimeters times meters, which isn't a thing. So you have to do it one more time. So you actually need to plug in 0.0025. Something to note, because in this chapter especially, there's a lot of squared units, meters squared, meters cubed. So, pretty drastic difference between the areas of the two sides, and that is in turn going to adjust the force input on one side compared to the force output on the other. Because the way that this machine would work is someone could physically press down on this cylinder, so they're exerting a force over this surface area that's going to push down on the liquid. That liquid's going to flow out into the reservoir and exert the same pressure up on the other side. But since that side has a bigger area, it's going to output more force for the same pressure. How much force would one need to lift this car? I already said that we have to exert a force equal to its weight. So instead of F2, I'm going to write in mass times 9.8. And we can figure out how much force we would have to push down on the narrow cylinder to make the car rise on the other side. 8 newtons. That's less force than it takes to lift this thing. You can lift a car with 8 newtons if you have a very complicated hydraulic system. So, by utilizing pressure in this way, you can basically multiply your strength, quite literally, which I think is neat. If anything works on hydraulics, if you've heard that word, this is what's going on inside of it. It's just liquid flowing through a piston. We use liquid for this because while liquid does not have a definite shape, it does have a definite volume. It's hard to compress water. You can try, but it won't go super well. Then for that reason, pushing down on the water doesn't cause it to shrink, it just causes it to flow out of the way. Whereas if there was air in here, pressing down on the air could cause the air to physically shrink rather than flow. There are systems that use gas for this. Those are called pneumatics instead of hydraulics. So pneumatics use the same principle, they just use gas instead, and they have to take a few shortcuts to make sure the gas doesn't compress beyond its parameters or expand beyond its parameters. Questions? All right. I will say there is one weakness to this sort of machine, and it's that this cylinder just has to be many, many times taller than the other one, because what's really happening here is volume flow rate. A certain volume of liquid flows out of here and into the other side. And since this one is wider, you know, a very tall amount of liquid over here is not the same height over here because of the area difference. So this side might point, you know, several stories into the air if you built it in a straight line like that. So people who are building systems like this have to be very careful and clever about how they manage that particular downside. But that's the last thing I wanted to mention for this chapter, just another application of pressure used in machines. And that's the last new thing I'll cover before the test next week. Questions, concerns, random thoughts? All right, yes.
You know, maybe test review.
Yep. On Friday, I'll probably start with just chapter 9 review, make sure this week sits good in your brains. And then we'll move into test review. My plan for the week is to get the updated practice test uploaded by Friday so we can look over it in class. And then again, the test is next week, but lecture time will be test review time. So even if you take the test Monday afternoon, Monday lecture will still be more practice. Any other questions or concerns for right now? All right, have a great day. Let me know if you need anything. Thanks.
Thank you.
Thank you.